great to see you all tonight. So I'm the geologist stroke educator for the Waitaki Whitestone Geopark. And yes, we're all very relieved that we can resume our public talks again here every third Thursday. So welcome everybody. And a big welcome to Nick Mortimer, who has come up from Dunedin. Nick is the lead principal scientist at Geological and Nuclear Sciences down in Dunedin with 30 odd plus years experience working in the field. So we're very honoured to have him here tonight. And this evening he's going to be talking to us about the continent Zealandia and revealing its secrets to us. So welcome Nick, we look forward to hearing from you. And Nick has said that he is open to people interrupting him for questions, so feel free to do that. And there are a few little handouts here at the end that you're more than welcome to come and collect. So there's maps and a wee field guide as well. So sit back and enjoy, and over to you, Nick.
Thank you for that introduction, Sasha. Thank you. I'm pleased Sasha said that I'm happy to be interrupted for questions during the talk, because that's something I always forget to say at the beginning of the talk. So stick your hand up, shout out, and if you want to ask anything. Going back a few months when Sasha first asked me to come up, we batted around a talk topic, because I know that you've already had some geologists in this talk series. You've had Brian Miller talk about Zealandia, David Barrell talk about Zealandia and Gondwana, and you're rescheduled Henry Gard to come and talk about the fossils. So I thought, well, what sort of point of difference can I offer? Because I eat and breathe and sleep Zealandia geology. It's very close to my heart. So I thought what I'd do is I wouldn't talk about the whats and the whens and the whys of Zealandia. I'll talk about the hows. Okay, so how do we know about that 95% of Zealandia that's offshore? So you've heard from my colleagues about the history of the rocks that you can hit with one of these and look at with the standard geologist's hand lens. But what about the offshore? Because the Zealandia being a continent is pretty much about the 95% offshore to make it big enough. And it's a big area, and it appears on the world map. We're very, very proud of that. Nice to see it there, a much better map for having Zealandia on. And so there we are, Zealandia, and the scientific evidence for continents. So we're talking about geology now, not geography. So you can see Australia has a bigger continent than just the shoreline. The scientific evidence for Zealandia is all basically to do with height, standing high above the deeper ocean crust. Have you got the right kind of rocks, granites and schists and greywackies and gneisses within the pink, instead of boring basalt on the ocean floor? And of course size, is it big enough? So all of this is to do with, we need to draw a line around Zealandia to define its size and the internal content that says, yep, this is a member of the Continental Club. So how do we go about that? A vast area covered in water. Well, so the two themes I want to talk about tonight are the two data sets I've used the most in my own work. And one is data from satellites up in the sky, and the other one is ships. Ships is more sensible, I guess, but there's various ways you can use ships. It's still a very big area. You've got to pick and choose your tools and your ships to do that. Yeah, so we'll start with ships, and then we'll quickly get into satellites, and then the last half of the talk will be ships again. I'll try and give you a taste of what life is like working on a research ship. And I've got a little movie to show as well. And if you like maps, you're in for a treat. And so this is not too technical a talk, all right? So there's no big scientific take-home message. It's more a background, looking behind the curtain at what scientists do with different kinds of data. Using Zealandia as an example. Well, let's go back to one of the classic Victorian-era research expeditions, this Challenger expedition. You can see from the map here, this was a 4-year voyage, and they went all around the world, north to south, east to west. And this is a true journey of scientific exploration, as opposed to Captain Cook style, geographic exploration. They were sampling the seafloor. They were taking samples from islands and things all around the world, and they were plumbing the depths, making sections and maps of the ridges, and just seeing how deep the ocean was, because nobody knew at the time. And so here's the crew assembled on the deck.
I'm sorry, you're probably about to get to this, but how did they measure how deep the ocean was back then?
Okay, it was with the old line.
Oh, really?
Yep.
Oh, okay.
Yep. Simple as that. Yep.
All right.
Yep. So I guess later on you'd have the pinging sonar methods, but not at this stage.
Okay. Excuse me. Strikes me that there should be some data from submarines. Do you not have access to submarine data?
Yep, I'll get on. I'll mention submarines. Submarines are pretty expensive. You've got to pony up a lot of research money.
Various navies and things.
Ah, the navies. Yeah. Okay. Okay. While we're on the topic, then, World War II actually provided a big injection of technology into the scientific research world, and that was driven by the military imperatives for better or worse. They would have done some surveying, but certainly, at least has come to my attention, it was the research work in the 1950s from some of the US research institutions that really invented plate tectonics and did lots of transformative things. So yeah. If we go back before the Challenger expedition, we are in this era of geographic exploration. I mean, the oceans are a blank sheet, just like this. And so the early explorers came to New Zealand. They found 2 islands that were larger than the other Pacific islands, but still an awful lot of sea there that was basically fairly mysterious and unexplored underneath the sea. So in the next few slides, 7 slides, I'm going to morph you the picture of a gradually more accurately appearing New Zealand coastline and shape of the sea floor around New Zealand. All right. So the earliest map of New Zealand that we have is Tasman's one, 1642, and that's all that his ship did. All right, that's where they came in. So that stayed in place for more than a century.
Wow. And I presume is that Taranaki, the sort of the nodule at the.
That's right. Yeah. So that's
and then the sounds, is it?
That's right. Yeah. So that's the west. That's northwest Nelson, Taranaki Bight, and up to Cape Reinga.
Okay.
Yep.
Is New Zealand just a sunken mountain range?
Yeah, it's a very good way to think about it. And as the talk goes on, yes, you'll see that coming through. And I hope you have a time to look at these posters at the end there. But you can think of New Zealand as just the tips of a sunken mountain range. Yeah, that's a very good way to think about it. And this map shows that. So here we see the first representation of New Zealand on the map. We're all probably quite familiar with this one. With Stewart Island as a peninsula and Banks Peninsula as an island. But still no detail from the surrounding area. So we'll fast forward again. This is from the Peterman Atlas of 1877. So these are very generalised maps. These are not the most detailed ones available. But here we see a lot more information, and I've colour-coded the water depth here. So the deeper the water, you get into the blues and the purples. Okay. So here we see the islands around New Zealand, the Chatham Islands, the Subantarctic Islands, Macquarie Island. They've all looked fairly schematically or loosely. They've put some shallow water around them, but nonetheless, this is a better map. We've got deeper water to the east and the west.
No, just I'm curious, when they were dropping down the measuring instruments, which was a chain, is that why it's called fathomless, the ocean? Were they using fathoms as a measuring?
Sure, that was 6 feet.
So
What's
they
that?
got,
Yep.
where it was like, we've run out of line, that's deep.
Yep.
So did they
so.
just say, what do they call that?
Well, yeah, we get all
That's
sorts of
deep.
we've got all sorts of metaphors from that, haven't we?
The uncharted depths.
Yeah.
There we go. Yeah. Hey.
Yeah.
Any more? Yeah. Yeah. Okay, another 40 years worth. So all of these maps are derived from these ships, okay? And so not every ship measures the water depth, but you know, a research ship would, the Navy ships would, hydrographic surveys, a country would be interested to know how deep is the water around it. So we're gradually getting a more and more detailed picture. So here we have Patrick Marshall was a geologist at the University of Otago, and he was interested in the Southwest Pacific and how New Zealand fitted in to Melanesia and Polynesia. So he published this map for a science conference in 1910, and he named this feature the New Zealand Plateau, because by that time I guess they had the confidence that such a thing existed. And if you can glance at that map there, you can see the Chatham Rise has emerged. Okay, the part of the Campbell Plateau here, and that ridge heading up north towards New Caledonia, as well as a very deep trench, the Kermadec Trench. Yep.
How did they know when the chain had hit the bottom?
Ah, very good. I don't actually know the answer to that, but I imagine they must have had some clever way to figure it out. Yeah, it's a very good question, isn't it?
What they had
Does anyone know?
was, yeah, they had a little cylinder, and it would pick up shells or sand or whatever.
Yeah.
So that's how they.
Yeah.
Particularly when they were approaching an island.
And the rope went limp.
Yeah.
Well, yeah, the Besom, because that blue there, you're talking 6 kilometres, right? So by 1910, somebody knew that water was 6 kilometres deep there. The trench is pretty remarkable. I'll tell you my own story about how long it takes to put something over the back of a ship and pull it in again in about half an hour.
In the map before, I had noticed that, see, there's all that tan, 0 to 1,000, and then it goes straight to green, which is 2,000 to 3,000. Yep. And then in the 1910 map, yep, we've suddenly filled in all the 1,000 to 2,000. Why? Do you know why it took so long to fill in that intermediate?
Well, I think I need you as my book editor next time for spotting things like that. It's just, you can blame this my graphical shortcomings. Okay, I mean, I probably did my best with the whatever contours they used. Okay. All right. Normally, I spin through these in 20 seconds, right? Okay. We're taking like 5 minutes for these, so don't get too hung up on details. So there's Marshall, and of course the next slide we're going to do a bit better. Okay. 35. Macquarie Island has been separated off. Things taking shape, and let's fast forward to 64. So this is. I'm not being 64 is of an era, so these maps are around in the 1980s still, okay? And this gives you an idea of the density of research ship tracks that sort of might have contributed to this. Obviously, the closer you get to ports, the denser the tracks, but the further away you get, there's plenty of holes out here, pretty flat ocean floor. So the resemblance between this and the modern maps is pretty good, and all of the features that were named on the modern maps were pretty much named by this time. The troughs, the rises, the ridges, the sea valleys, the big seamounts, that kind of thing. Yeah. But we can do better still, right? So up till now we've just been dealing with ship tracks, and we interpolate or average in between the ship tracks to make this map. But the big increment, and what's been really, really useful to us in getting out and exploring Zealandia is getting the seafloor depth from satellites. So this is my colleague Vaughan Stagpool's map. It was made in 2002, but the earlier versions were around in the mid-1990s. Right? And as more and more satellites get launched that measure microgravity, and I'll explain about that in a minute, so we're getting better and better resolution maps of the ocean floor. And the great thing is that nothing can hide anymore, okay? Previously, if you had a gap between ship tracks, you might miss a big seamount or something. Now we have 100% coverage of the ocean floor, and so nothing can hide, all right? And we can see the shape of things a lot more accurately than we could before. So we're going to stay with this kind of map, and this has been really, really critical to us, literally seeing Zealandia jump out of the page at us. So the red line is the continental limits, if you add the black plate boundary on there, between the two kinds of crust, continent and ocean, and the plate boundary, you can pretty much explain every major geological feature of modern-day New Zealand with all those differences on it. So the continent, you can see inside the red outline, we're in the yellows, and so it's higher than the deep ocean crust, and that's one of the main features of actually calling something a geological continent. And it's the satellite era that's given us the accuracy and precision and the continuity to say this.
So, sorry. Why are the two ridges that head out like that not included in the continent?
Yep. If you can wait till the penultimate slide of the talk, I'll show you.
Yes.
That's got to do with the rocks. Okay. So height is one thing, but within that high part, we have to find granites and schists and gneisses and greywackies. And we haven't found them yet along those two little yellow strips.
Yep.
And we've got good reason to believe that we won't.
Okay. All right.
At least not yet.
This is what you get for encouraging questions.
Yeah, that's precisely. This is great. This is really good. Yeah. So there's lots of different versions of this. Niwa put them out, different colour ramps, different times, different areas. The Niwa cut those pretty close to New Zealand. GNS tends to go further north and south. Even Google Earth has a kind of a dark blue colours in the sea. They're all derived from the same digital data set, which is open filed, it's public domain. You can download it yourselves and play around with it. And in the last slide, I've got a link if you want to go and explore these sort of things. So they're mainly a mix of American and European Space Agency satellites. And yeah, thanks to the taxpayers of those countries, we can benefit in New Zealand from these data sets. So how's that done? How does a satellite tell us about water depth? Well, it doesn't actually give us a bathymetric map. So by bathymetry, we mean the topography, the hills and the valleys of the seafloor, right? So it's a fancy word, but it just means hills and valleys, but are under the sea. Normally, these are out of sight. What a satellite can measure is the pull of gravity, all right? These are like GPS satellites. Their position is known very, very accurately. If they deviate from the position, it can be measured in time and in space, and the amount of the deviation can be measured. So when a satellite goes over, when it's the pull of gravity is higher, it moves down a bit, and that is because of a few reasons. Either there's a mountain like Mount Everest underneath it; it's closer. The Earth is closer to the satellite; it gets pulled down, or you've got a very dense rock there, or both. So this map on the left is the actual microgravity, and at sea level, gravity varies by about 5%, which is quite a lot, really. Okay, in terms of the weight, if you go over different parts. So the red parts of the map is where gravity is high, and the blue parts are where gravity is low. Yep. Got a question?
Is there a taller mountain than Mount Everest under the Earth?
There is not. No. Mount Everest is the tallest, is the highest point on the Earth's surface, including the sea. Yep. So the high gravity is red, and you can see there's a rough correspondence between the bathymetry. So where we have very deep water in that Tonga Trench, the gravity is low because water is less dense than rock. So the satellite's going over lots of water. Anyway, there's a lot of clever mathematics involved in turning that into that, but that's basically how it's done. It's pretty good. These are actually merged with ship tracks, so there's a certain amount of ground truthing as well. And so you don't just take the word of the satellite up there, you actually cross-reference it, and you can come up with the corrected bathymetry map like that.
So are we supposed to assume that, forgive me if I'm preempting some of your other slides, but the area that's currently underwater, is the presumption that at some stage it wasn't, that it was above sea level?
If you go back 100 million years, the answer is yes. It would have been part of Gondwana, and
Yes.
from the geology, we think it would have been growing trees and been on land with rivers going across it. But it's been submerged for a long time.
So when did it submerge, and is that glacially related or not?
No, I mean the most recent sea level changes and ups and downs are glacially related. That's 1 to 2 million years ago, rather than 100 million years ago. So, as I say, that's a separate talk. But it's a good question.
On the end of that question,
Yeah.
Banks Peninsula was once a volcanic island set up, a cluster of volcanic vents, wasn't it?
Yep.
And wasn't actually physically attached to the mainland. or
That's
was it?
correct. Yeah. No.
Yeah, so when did that happen?
Yeah, that's the connecting Banks Peninsula to the rest of the South Island is fairly recent. Since the ice ages, the gravel plain's gone out to meet it. Yep. Yep.
And I've got one question, sorry. So is the continent going up or down? Or is it always going up and down?
Your last statement is correct. Something's always on the move. Okay. It depends on the way the plates move together or pull apart slightly, that things can go up and down. It doesn't actually take much of a change in pushing direction to force something up versus down. And sideways, of course. There's sideways is a big movement. Right, so that's how we get there. Now we can do some. These were the starting points for making these maps here. All right, so the bathymetric map's fairly simple. We just take that, put a nice colour ramp on it, add lots of names, a bit more decoration, and there we go. The geological tectonic map requires a bit more interpretation, and so we can actually do some interesting tricks and tweaks on both of these maps to highlight the edge of the continent and to emphasise volcanoes and to see where faults are. So the next few slides show you that. So remember, we're still dealing with satellite data. So these are different ways to look at that bathymetry map, all right? So on the left there, we can pretend that the sun is in the southwest, so the bottom left, and we can put it low near the horizon and shine it. And so we can get these shadows lighting up. And so we're doing this on the computer screen, right, in a GIS. And so we can put the sun wherever we like, and it's amazing what turns out. You can emphasize things and see things that you don't normally see on a kind of a flat or a normal contour map. And yeah, we can apply an algorithm. We can differentiate. Anyone remember differential calculus from school? Yeah. So the first vertical derivative of depth gives you the slope. So wherever there's a white line on this map, it's a steep slope. All right. And wherever it's black, it's flat. So you can see this volcanic chain emphasises, and also the edge of the continent, the edge of Zealandia, nice and sharp here. So where there's steep slopes that we might be interested in geologically, this is a nice way to see them, and we can digitise that line and put it on the.
So I've misinterpreted those two. I'm looking at that one, that diagonal bit that's sort of one its way down and tipping up the page.
Yep.
I assumed that was a treat, but what you're saying, looking at that one, that's actually a ridge.
Yep, that's right. You can just see the there's this one here, the line of yellow volcanoes. Yeah. Come and look at this later on. Yeah. But it takes that kind of looking and getting rid of any assumptions to find new information. So that's what you can do with the bathymetry, and you can reveal the faults, the fault pattern down here. Also, there's a lot of noise on here. You can see some ship tracks emerging as well. You can see some radial lines coming from Wellington, hereabouts, and from Auckland up there. So this is this merging of the ship tracks with the satellite data. It isn't perfect. And likewise with the gravity map, we can do that first vertical derivative again, get the gradient of the gravity. And here we're looking at nice textures. So continental crust is got a bit of a texture. Ocean crust smooth here, faults. So there's all sorts of things light up. And not only do we have gravity to play with, we've got magnetic maps as well. And these two are a mix of satellite data. There's satellites up there with magnetometers on, whose sole purpose is to measure the Earth's magnetic field. And the towing a magnetometer is pretty routine for a research ship as well. So this map here, you can see our local New Zealand area with research ships. You can see it's a lot more sharper in the middle, and then the very top and the very bottom of the global coverage. It's a bit more fuzzy. But again, all sorts of interesting rocks. More magnetic rocks in red, less magnetic rocks in blue. And a geologist can start to match those with these rock types that we want to find within continents.
So magnetic suggests it's geothermal or volcanic?
More to do, sometimes, yeah. Sometimes geothermal activity can wipe out a magnetic rock. As it turns to clay and gets soft and alters. That's what my colleagues find up near Rotorua and Taupo. That you tend to wipe it out. But basalts and granites tend to be very magnetic, and schist and Waitaki, not so. So this is the last slide dealing with satellites now, and then we get onto the shipboard life. Okay, so there we go. So based on mainly on that satellite gravity and bathymetry data with the help from magnetics, we can come up with a map like this, where we've outlined the edge of the continent, where it's nice and sharp on some of those, and there's nice little white points with the steep slopes are seamounts that we think are volcanoes. So on a map like all these dots appear as tiny symbols on this map when you get your nose up against it. Zealandia, the shape of Zealandia stands out a lot better. So there we go. That's kind of how it's done. All right, from a desktop instead of waving a hammer around. But
so with that line of volcanoes on the right there, the very long, slightly curving line that heads up to the Tongan Trench.
Yep.
Would that have been the original location of the plate boundary? Because it just looks so precise, and yet your earlier map showed the plate running basically through the South Island. So why that line of volcanoes?
Yeah, that's what's called a hotspot track. So that's there's like a hotspot coming out of the Earth, deep in the Earth's mantle today,
right.
And the plate is moving over the top of it in the same direction.
Yeah.
And it's like a candle burning a black line in a piece of paper going over the top. Okay.
So the plate must have been
the Pacific plate is moving that way.
Yeah.
And there are some tracks on the Australian plate. These ones, the Australian plate is moving straight north. You can see these chains here.
Yeah.
Over the mantle.
Okay.
So it's a nice. There is an explanation for them, yeah, but that's independent of where the plate boundary is between them, yeah.
So it's like a contrail of.
That's another way to look at it. Yep,
Yeah.
yep, sure,
Okay.
or a breadcrumb trail if you like.
Yeah.
And the volcanoes all get younger in one direction. Yeah. Anyway, being a good empirical scientist, I'm a firm believer that you need to test this, all right? This is all very well to put out there, but how do we know? I mean, does it have the right rocks that I talked about, okay? And this is where we actually need some rock samples, all right? And so we do need ships still to go out and try and get some. And there was a question earlier on about, or a point made about submarines. And certainly there are some research submersibles run by the Japanese and US institutions, whereby you can create a research proposal, and you can fit 2-3 people into a submarine and go down and then pick your way through. That's just brilliant. That's kind of the creme de la creme of submarine geological investigation. But it's extremely expensive, and so few institutions have that sort of capability that it's something I've never done, and I never expect to. Cornel Durand, one of my colleagues in Lower Hutt, he's been down on the Kermadec volcanoes in a submersible.
I was more thinking about their navies, because they obviously need to know where they're going.
Yes.
Water, they don't have portholes, so they should have very good maps, I would assume, of depths.
Yeah, I think you're right, and if I can just digress another brief of the search, that Indonesian plane MH370, was it? Mm-hmm. There was an intense bathymetric mapping effort put in to try to find the plane of that part of the Indian Ocean. Much higher resolution than anything I'm going to show you today. So yeah, the text there, I guess you need the purpose though to do it. The Navy, well, the New Zealand Navy does operate a survey ship, so certain wings of the Navy do this kind of thing, but
I
I've
just
never.
think it would be useful information for
It would.
us to know.
Yep. Yep. Anyway, so you can go in a submarine, but not many geologists do that. Likewise, drilling. I mean, oil companies have got enough cash to splash to drill, and there are research drilling consortia as well operated around, and they're very good. And you can actually put up proposals. And again, many of my colleagues have been co-chiefs on research drilling expeditions around New Zealand. Yep.
Is the research drilling harmful, like oil drilling?
No, I mean they always take as much care as they can with the drilling, and but in terms of the research rocks, they're not drilling into oil bearing rocks, so they're drilling other things. But the tool I've used is dredging. Okay, very much like a sand dredge in a harbour. And I'll show you how we do it because that's what the movie's about. How we get rocks off the seafloor. It's very, very simple, very low tech. It's still quite expensive to buy time or to get time on these research ships, but there are quite a few of them. Almost every Western country runs a research fleet of some sort, including New Zealand. NIWA is the organisation that has our sort of deep sea research capability. So I've been on 6 or 7 research voyages in my career. These are three of there's a couple of Australian ones on the left, the French one here, and I'm going to show you some slides from the French expedition I was on a few years ago. So again, I'm not going to explain about what we got, or why, or what it means, but just how we did it. Give you an idea of what life's like on board, and how we can get rocks off the seafloor to test these maps. So we're still taking pictures of ourselves on the decks of ships. It's a thing to do when you've got an expedition, right? You do it. So, yeah. But as I hope to communicate to you, they're delightful things. There's a great sense of camaraderie and purpose and focus when you're on board. And they're very memorable and for the most part very enjoyable things. Not like a holiday cruise, I should add. I'll explain a bit about that too. But it's great to come together. Everyone's got the same purpose. They've come from different countries, travelled to be on the ship. The ship's crew, the captain, the cooks, the deckhands, the engineers, they're all there for the sole purpose of making your research cruise a success. So everyone's got the same thing in mind. So this was a French ship, l'Atalante, and the whole thing was about 6 years in the planning. All right. So from the start, the first proposal we submitted and failed, knocked back, tried again, no luck. Tried the third time, successful. Went into a waiting list for ship scheduling because l'Atalante's mainly based out of Brest in France, but they did schedule some Pacific legs, and so eventually it happened. And so we had 3 to 4 weeks, starting and finishing in Noumea. So the first thing what you notice when you get on board the research ship are these sort of things. You've got to find your way around, and long corridors, lots of stairwells, and so after 2 weeks you finally do know your way around, but you're always going up blind alleys. And another curious thing, these boots here mean someone's asleep. All right. So ships are 24/7 operations, and we organise ourselves the scientists into 2 12-hour shifts. So you're on duty for 12 hours, and then you can sleep and do other things in the other 12 hours. Sometimes they are 8-hour watches. It just depends how many people you've got, that sort of thing. Next thing you do when you get on board the ship is this. You run through the health and safety drills, putting on these immersion suits in this case. With time, these get more and more stringent. I mean, when I first started going to sea in the late 90s, these are pretty cursory, but of course we take health and safety a lot more seriously now. And this is the sort of accommodation you get. Double bunk berths. If you're senior enough, like I was, a co-chief, you score a single one, which is nice. But otherwise, you generally share a room with someone who's on a different watch to you. So when you're up and about, they're asleep, etc. A little desk there, a toilet and a wet shower. So yeah, very, very, very compact, but it's all there.
So doesn't that make it hard to go about doing anything in your room if your roommate is asleep?
It does. So in your room, you basically sleep.
Yeah.
Yep.
Okay.
Or have a shower. Yeah.
Okay.
Yep.
What was the food situation like?
Ah, right. What's the food like? I'll show you in the slide after this. We'll get to the mess. Yeah. But here we're up on the bridge. All these pretty much look the same to me. There's Martin, my co-chief, second mate, and one of the deckhands there. And yeah, it's at the top of the ship, nice view. It's all pretty open. Nothing's off limits, so we often go up there. And when we're dredging rocks, there's some pretty key stuff going on here. All the winches and things are controlled from up here. Yeah, so this is a very important place on the ship is where you eat. So we are there again. They all have the same look and feel, but the mess on l'Atalante, my colleague Lionel Carter once described this as a French restaurant surrounded by a research ship. Because yeah, the food is very good, as you might hope and expect. Yep. It's good. Even though it's on wooden trays, it looks pretty canteen-like, but it was definitely a cut above anything you get on a Tangaroa, I have to say. Yeah. And what else can we see here? Yeah, there's a kind of a I didn't really take any photos to show. The sauce bottles are in these kind of wooden boxes. The skirting boards, and likewise the bottles there. So, obviously the ship does do this, right. But people still need to eat. So, there's precautions taken there.
Right.
And this is when you're awake, and so this is some of the scientists here doing their stuff. So there's a workroom, operations room as we call it. So we have a nice big room we can spread out the usual array of computers around the edge. Keep an eye on what's going on, which way the ship's going, and that sort of thing. And here we've got lots of maps spread out, the same sort of colour spectrum ones that you're used to now from this talk. Water depth, shallow is yellow, deep is blue. We're figuring out where we're going to dredge. And these are some cross-section charts of the seafloor that the ship's been over previously that we will turn around and go back to and get some rocks from. And yeah, so digital ops very important. We've got on board GIS, and you have these kind of arrays of flat panel screens now. So it is a very digital place, and that's near a porthole, but often these are down in the bottom of the ship. These sort of things. And 24/7 out on deck. We're getting closer to the rocks now, because that's why we're there. This is the night shift. Getting ready for a dredge to come on board. So yeah, hard hats and fluoro vests and flotation jackets are a must. And you see plenty of these, twice a day. They're there for free. Just drink them in. I mean, it's that horizon out there. It goes forever. It's marvelous. And occasionally the sea is as calm as this. Usually it's not, but it's always a lovely, moody somehow. Okay, and another thing is you get a great, I get a great sense of progress on a ship. It's always going somewhere, or if it's stopped, it's always doing something, right? There's always something going on and something to pay attention to. So here we are, we're underway. These have a top speed of 12, 15 knots. What's that, 20 k's an hour or something like that? And we're towing a magnetometer behind us. On this, we're in transit between dredge sites, so we make maximum use of just even a kind of a random transit. We tow it's measuring gravity, it's measuring the seafloor bottom, and we're towing a magnetometer here. And the back part of the ship is where you usually where we geologists dangle a lot of things off. And I'm going to show you the dredging in a minute, operational on the back of Lac Lance there. So, we do more, we don't, all right, the point I'm going to make is we don't just go out of Noumea and think, oh yeah, what are we going to do, you know, where are we going to go? It's very, very purposeful. And this is a map, we'll spend a few minutes on this map of the voyage that we did, right, from Noumea to Noumea. This is 500 kilometres scale bar here. New Caledonia is the black land in the top left there. This little fly speck here is Norfolk Island. Okay, and there's no other land in sight and here.
Wow.
But you see they have names: South Fiji Basin, Three Kings Ridge, Norfolk Basin, New Caledonia Trough, etc. Okay, all these major ridges have names, and this pink and black zigzag line is the track we took over that 3.5 weeks. And you might think, oh, what the heck were they doing? Why did they suddenly turn right there and do this or that? Well, the pink is when we were shooting seismic lines and towing that magnetometer. And the white dots are where we got rocks off the seabed. So we deliberately headed down the Norfolk Ridge, did some surveying, did some dredges there, came back. This is our main work area. We did a pass across there, up and back again, zigzag, and then we came back and dredged rocks along the track that we'd previously been on. That's how it worked. And yeah, as expeditions go, we sort of got up to 43 separate times we put the bucket over the back of the ship and got rocks, which is a very productive trip for us. And as we go, we make maps as we go along. You've seen that one before. The spiky rocks with the kind of the muddy, oozy sea bottom in between. There's no point in trying to get rocks off these flat, muddy bottoms. We want to go for rocky peaks to get rocks. We make our own very detailed bathymetric maps of the local sites. When we think the ship will circle around, spend 2 or 3 hours surveying a very small area, and then we lay some plans in and lines in where we want to try and hit the sea bottom. So there's a lot of preparation work even when you're on board, and yeah, these are what we want to try and do. But possibly I should have put this earlier in this talk, but this is what a rock dredge looks like. Right, this is what we send down to the bottom of the sea. It's very old tech. It's been used for more than a century, but it's still tried and tested and very effective. So what we've got here is it's basically a steel chain mesh bag, all right, with a rim with big pointy teeth on it to try and break rocks off, and a yoke that hinges, and then it's attached to a cable with like a 20-ton breaking strain, steel cable. Wow. And so this gets wound off the back of the ship and until it hits the sea bottom. How do we know it hits the sea bottom? Because there's a meter on the bridge that shows the tension on the cable. And so when the meter goes up, we know it's hit the bottom. And after a while, we bring it in again. The deckhands turn it upside down and hopefully dump some large rocks on the back deck that we geologists can look at. So that's how we transfer rock from. It'll be a line on the sea floor. So the ship's moving ahead at about 1 knot. It slows down when this is going on. Moves forward very slowly, a slow walking pace, and yeah, we're literally just dragging this bucket along the sea floor, hoping to break and collect rocks.
So do you get wildlife?
Usually, the depths we've been working at, usually not. I mean, we do get some, yeah, occasionally bits of coral and that kind of thing. Yeah, dead coral.
So you're not concerned about destroying an ecosystem down there?
No, not in this case. No, they're very. It's a very narrow trail. It's not like bottom trawling with orange roughy or anything. We're not kind of mowing the grass or anything like that. And we do have the research permits from the necessary authorities to do it.
Well, I'm interested to see if you're getting any treasure chests.
Yeah, I wish. I wish. Anyway, the next slide. Yes, okay. And so this is what we can do. We can get rocks on the back of the deck, and then we can actually use one of these, like we're familiar on land to break things up. But the next slide is the movie, that's right. So I'll run this. This is a time-lapse movie. It's sped up 10 times. So we're going to look at 20 minutes of activity on the back deck, compressed into 2 minutes. Okay. So what the story is that that dredge has been down on the seafloor. It's been off the ship for the best part of 3 or 4 hours. Okay. The winch pays out at 1 meter per second. So to get down 3 kilometers, you're talking about the best part of an hour just to get the thing on the bottom of the sea. Then you want to drag it along for a little bit, an hour, say. They do get stuck, in which case the captain doesn't like that, but they do come back. And then you've got to wind it in again, which takes another, depending on the water depth, can take hours.
So you said you dredged for about an hour. What
Yep.
sort of length of dredge line would you
It'll be about a 1 or 2 kilometres, probably. Yeah. Yep. All right, let's go. So say this is sped up, and you'll be thoroughly seasick at the end of this, I would think. So great, here comes the dredge. Great expectation. So has it got any rocks in? Sometimes they come up empty. Sometimes they're chock full. Sometimes the bag breaks, and the rocks obviously we've got some of it emptied out. Here we come. So all the geologists are standing behind the camera here. All right, we're not allowed to go in there yet. Here it comes. Oh, that's pretty. Yeah, that's pretty good. So now they're securing it, and they'll invert it. Good.
So it's not about pinpointing a particular type of rock, it's getting a general overview of what's along.
Very good. Yeah, that's excellent. Because this is just the reconnaissance work, really. At the scale we're working at, the whole of Zealandia, we're not too interested in the exact thing. Yeah. So here we go. The ship's turned around. You can see the shadows change. It's already off to the next place. But the geologists are all over the stuff now. this is what, and we're putting looking at, is it all one rock? Are there different rocks? We're putting them in these plastic boxes to take back to the lab. In this case, it was all pretty much the same stuff. So we have a big pile of rock. We don't need to keep it all, but we want to keep the best bits, particularly if there's any fossils and things in there. So we're having a look. There's the old hammers out there. Taking things back, and so we're pretty much chucking stuff back now, where it came from.
Some poor fish gets a headache.
Yep.
Oh, I'm just swimming along and off the big rock hits me.
So these same boxes. So we just walked along the deck into the lab. It's a kind of a dirty, wet lab. We can clean the rocks up. We have a rock saw on board, so it's much better to see on a clean cut face what we've got rather than a black wet rock otherwise. So there we go, and so after every dredge, Vesper dredge 27 here and 29 there. We sort them out into different kinds of rock, because basalt, andesite, limestone, sandstone. Just very basic sorting, and all this gets recorded. And there were scientists from France, from New Caledonia and New Zealand on this voyage, and different rocks go to all these different institutions. So that's another reason they were very careful with the cataloguing of them.
There have been several studies all using that information. Like obviously you had your own sort of study that you were doing, but you weren't the only ones there, right?
Right, okay, so I think how most voyages work is that they're usually dedicated to one particular activity, like oceanography or biology or geology. So it's pretty rare to actually have multidisciplinary cruises. in my experience. I'm sure they do exist, but if you did do that, then you'd have a lot of people twiddling their thumbs for a lot of the time, because no other science topic would use rock dredging, for example, or seismic work, and we're not interested in water temperature. So that's I think they're pretty focused. Whether that's the best use of ships, I don't know, but that's how it works in my experience.
But you would have a different set of questions to the guys from France?
Complementary. We know that they've got the analytical kit to do certain things, and we've got the kit to do other things, and so that's all planned beforehand as well. Yeah.
So any papers that came out of this, you would all be authors on?
Yeah. That's all by agreement as well,
Yeah.
by pre-arrangement.
Yeah.
We do a limited amount of analytical work on board. Patty's got a portable X-ray fluorescence machine for some compositional work, and Hamish is looking at some microfossils under a microscope. But there's not a lot we can do on board. In fact, we're so busy, stuff's coming on board, twice a day normally. So all that cataloguing and soaring and cleaning up takes time. So we really only got time to sort it out. But these are the sort of things we see. Very, very nice, pretty rocks.
Wow. Yeah.
On the cut face.
Do you get any rare earths?
One thing we do get a lot of are these manganese crusts, these black crusts on everything. These manganese oxide crusts, they've got a lot of metals in them, things like cobalt, chromium, that sort of thing.
Of an extractable quantity?
It depends. That's an economics question, not a geological one.
Right.
But I mean, geologically they're there. I mean, there's lots of them in the Pacific Ocean. These manganese rinds and nodules and crusts. But it's just not economic to mine them from the seafloor. Maybe it never will be. Right. And the other thing is we get there's some pipes attached to the dredges. So obviously in that chain bag, you only get pebble-sized bits or bigger. All the sand and mud kind of just flows out, except there's some pipes attached, and so we get this ooze, this calcareous ooze mud. And you put your hand in there, and it's cold. Really, every time. So the bottom of the seafloor, the water's only about 2 or 3 degrees centigrade. So
Given that is made up also of all the detritus that's fallen down to the bottom of
Yes.
the sea, when you bring it up to the surface, does it smell?
no, because it is dead. You're right. I mean, the living organisms are in the photic zone. I guess they sink down. I don't know how old they'd be, to be honest. I mean, some of them would have been there yesterday. So, but no, I don't recall any smell. No, not really. No. So it's kind of mud, muddy sand. Yeah, is a consistency. You can see the individual foraminifera. They're less than a millimetre diameter. There's lots of mud there too. And at the end of the cruise, we're not smiling, are we? But we're very happy to get this kind of quantity of material. This is all of it kind of on the pallets, ready to go. Some to France, some to New Zealand, some stays in New Caledonia. And then the work begins here, really. I mean, there's a whole cascade of analyses, thin sections, isotopes, and then there's the figuring out what it means, and then the write-up, and then those papers are used to make the tectonic map. Well, that's how it's done, or that's how I've done it in the voyages I've been on. So yeah, very, very, very productive. And so, this is the current, if you like, the rock count from offshore Zealandia. Every place there's a coloured dot there is where we've got a continental rock. Things like granite, diorite, gabbro, rhyolite, grey schist from around the place. So this is a mix of dredges, petroleum industry boreholes, research boreholes. I've actually been I've covered in some of the subantarctic islands as well, just for good measure, because there's some rocks there that can help us with these points. Yep, you got a question?
Do you know the rock that you showed us that had the black stuff in it?
Yep.
There's a similar thing, or it might be the same thing, down by like the beach.
Right.
the beach down there.
Oh, okay. Yeah. Well, quite likely. I mean, you can get this rock here is one we dredged on that cruise. Okay, if you're interested. So you can see the black rind on it. Most of it's fallen off or spalled off. It's just the thin interior bit. I mean, rocks can be different colours for different reasons, but yeah, black rocks locally, sure.
Yeah.
This is a lava with some nice plagioclase crystals in, and yeah, I say just it's been handled so much. There's just a thin manganese rind left on it. But you're welcome to come and have a look at that.
Is there a pattern of depth that correlates with the rock types?
Not well, actually, it's sort of. I mean, I guess this shows us in that we're getting the continental rocks from Zealandia, which is high. Having said that, that's kind of biasing the answer a bit because most of these deep water abyssal plains are covered in that ooze anyway. So we would have to drill through that to get any kind of rock. And I haven't shown that there are some research drill holes in the deep sea floor, but I haven't shown them on this map either. So.
What about underwater geothermal activities, springs? That sort of thing?
Yeah, well, of course, that's not a Zealandia focus, but some of my colleagues go after those up in the Kermadec Islands. Yeah, so
there's none in evidence in the Zealandia?
not in the ones that we've done. No, all of the rocks we're after are old and cold. Yeah. There are such things up in the Kermadec chain of volcanoes, active volcanoes up towards the Kermadec Islands and Tonga, and in that northern basin up between Fiji and Vanuatu. Yeah, that's where the undersea kind of volcanoes.
So even the Bay of Plenty, where you've got White Island tiki-touring out from
Yep.
across from White Island and on, there's nothing following a pattern going up or out from that point.
Oh yeah, I mean, well, there is. You can not that shows up on the map. If you get your nose on one of those on this map, you can probably you will see this chain of volcanoes, which equals heat, and hydrothermal activity tracking down into Mount Ruapehu, who's the southernmost volcano of this really long chain that goes all the way up to Tonga.
Okay.
So that is a line of active heat.
Yeah.
But it's a different story from the Zealandia continent
So
story.
Taranaki is separate in a separate
Yep.
setup from Ruapehu.
It is, yes. It's offset. It's way back. It's got some companions in other volcanoes. If you get your nose on the map here, yeah. Curious one, Taranaki. Okay, so yeah, remember the reason we're doing this is to check these maps, all right, to make sure that where we put the red, that we are not every time, but sometimes get these continental rocks, and where there's a black dot that we picked from the gravity map, that we do get basalt or a lava from a volcano, and if we don't, of course, we can change. That's interesting, right? We can change things accordingly. All right, so that's pretty much the end of the talk, but I've got a few concluding comments. Hopefully you've had some insights into how we go about our work offshore, what we do, the kind of data sets we can bring in to get this big picture. And the kind of things we do with this is GNS, we've made these two posters. One that shows the bathymetry of the offshore Zealandia, and one that shows the geology. These were published last year, so they're new. They're the latest word on what's out there. 10 years time, they'll be different. All right. They'll
So the Alpine Fold.
Yep.
I understood we were going underneath, and the Zealandia plate was going underneath the Australian plate. So, are you saying that Zealandia is actually part of all that yellow stuff around New Zealand?
Yep. So Zealandia here is cut by the plate boundary. The plate boundary goes through Zealandia, the middle of Zealandia. In fact, we call this North Zealandia and South Zealandia, rather unoriginally. And
so they are two separate plates.
Yeah.
In effect.
So the idea is that a tectonic plate boundary can break through anything at all, any kind of solid rock, be it ocean crust or continental crust, and they do all over the world. They don't, obviously they don't care if it's continental or oceanic, but they cut across them.
So
So Zealandia was there first, and then the plate boundary came along and cut through it.
So continents are not, continent boundaries are not formed by plate boundaries.
No, sometimes these things form along the edges, but not always.
But not always.
Yeah.
Okay.
The continental crust is different to the crust that's under, it's not continental.
Yes.
And it doesn't matter whether it's under the sea or not.
That's right, yeah, and I haven't touched on that in the talk here, and I could produce some slides that would explain that better.
Right. Yeah.
So
But the two kinds of crust, continental and oceanic, are the two fundamental geological kinds of crust.
So Zealandia is only about a third of the mass of the Australian continent. One
Yep,
island.
that's right, yeah, but we still think it's big enough
Yeah.
Yeah.
to be called a continent, yeah.
Okay.
So, much as I'd like to give everyone a copy of these, I can't, but I've got the cut price versions, so I've printed off A4. If you get a magnifying glass on these, you'll just about see enough detail, and there's actually a website you can go to, it's written on here, and we've got these as web map versions, so this is what it is. So if you can zoom in and you can pan around and turn layers on and off, and so you can be your own desktop geologists.
Nice.
It's a nice thing to do. And if you're interested in the raw data and all of these global data sets, something I've got on my MacBook here is this thing called, if you put that into the a search engine box, you'll get to the website at Lamont Doherty Research Institute in New York. And you can download the app. It works on Windows or Linux or Mac. And it's a kind of a cut price GIS, basically. But it comes ready packed with ready connected to all these different magnetic and gravity and bathymetric and ship data sets. So that's certainly for the keen, right? I'm not suggesting you all do that, but if you really are interested in getting into this, then that's a source I've used. Yep.
We stuck those maps at Vanish World.
Great,
GNS
that's
maps.
great to know. Yeah, to know. I know you do really well for GNS publications there, so thanks, and that's good to hear. So if you want to buy these, Vanish World, that's great.
Okay. Cool.
And there's also a few little Zealandia notebooks here as well.
Ah, nice.
So there's maybe not enough for everybody. So be kind.
Yeah.
Would it be safe to assume that Zealandia broke off from Australia? I mean, it looks there a bit like some of the other continents you see, that Africa joins South America and so on. I mean, can we assume that Zealandia broke away?
Yes, probably more than assume, actually. Yes, I think we could say it's been demonstrated.
Right.
Yeah.
Okay.
So, following on from that then, just out of curiosity, as I understand it, the closest relative to the kiwi is a bird in Mauritius, and the closest relative to the moa is a bird that flew, a bird able to fly in South America. So at what point was this, I mean, when was the last possible time that the ancestor of either or both could have hopped from one place to another?
So the number that's batted around a lot, when Zealandia as a landmass, not submerged but as proper land, was joined to the rest of Gondwana, meaning Australia, was between 85 million years ago and 100 million years ago.
Yeah.
Yeah.
So it would have to have happened sometime around there.
Yeah.
Yeah.
But you've got just the person coming in July, Henry Gard, who's a paleontology colleague of mine. So you can put your paleontology and flora and fauna questions to Henry. He's much better equipped to answer them than I am.
Okay, so you were going to say why the two ridges there are not considered part of the continent? You said they don't have the continental rock, and you don't expect to find it there. Why don't you expect to find it there?
Because we can explain those two thin ridges by our geological understanding that they're formed by subduction. They're just young volcanic chains related to that subduction zone, related to the trench.
Okay.
Yeah.
All right.
I mean, if we did find a granite in Fiji, say, it'd be fantastic. We'd push those red lines out, or give it its own Fiji microcontinent or something like that. That's what we do. But so far, no, there's been many expeditions up the Kermadec Ridge, because of the volcanoes there, but none of them have come back with any of these rocks.
Okay.
Yeah.
Okay.
Oh, Nick, I'd just like to there's one more question, yeah?
I've been trying to track down your book, Zealandia.
Ah.
Is it out front?
I'm afraid it is, yeah. Hamish and I are slightly miffed that Penguin never reprinted it, but it's been out of print for many years, and GNS has run out. I get asked that question about once a month. You know,
Really? Oh.
And
You should tell Penguin then.
yeah, no. If you can find one, good luck to you. I wish I could help. But,
Yeah.
If we put in an order for 1,000, will they go back and print it?
oh well, yeah, they might do. Yeah. We've kind of moved on. We're making these New Zealandia products now as well. So and there'll be other things come out in the future.
There may be libraries around New Zealand that do hold a copy, and we can access it through our interloan system at the library. So it's very
Thanks,
fast.
Debbie. Yeah.
Is Tasmania volcanic?
No.
It's not.
No.
Because we've been watching a program, and see where the dark rusty brown is in Australia there, just inland from Sydney. There's a lot of volcanic stuff in there.
Okay. When I say no, it's not volcanic. There are no active volcanoes there. I mean, it has very old, Cambrian volcanic rocks as part of the mix of rocks there, just like the Tasman district does, or even Southland. So there are very old, cold, chopped up volcanic rocks. But you kind of find those everywhere on this kind of scale, though. Yeah, volcanic rocks.
Yeah. Maybe just one more question down there, and then we'll call it a night. Have another question, Alex?
When you were doing the dredging, have you ever pulled out more than one type of rock?
Yep. Oh yes, we have. That's a real bonus actually. The example I gave of that big pile of brown stuff, we picked through it. It was all the same, which is why we threw most of it back. But the best kind of dredges on the deck are where you've got 5 or 6 different kinds of rock, different kinds of lava, limestones. Fossils are always popular everywhere.
Yeah.
And although mainly they're micro fossils that we get, but yep.
Okay, so I'd just like to thank Nick very much for coming along this evening, and you've whetted everybody's appetite. I think it's created a lot more questions, so we might have to get you back another time. Here's just a little bag of local goodies for you.
Oh, thank you.
Thank you
Thank you,
very
Sandra.
much for
Thank
coming. And we will put on our Facebook page these links for people to connect with, and do come up and grab copies that Nick's very kindly provided this evening. And these maps are available for purchase either through Vanished World or directly through GNS website as well. So our next talk will be on the 15th of next month, and we're having some people come from DOC to talk about limestone ecosystems. So a bit of a move from geology, but for next time. So thank you very much all for coming, and safe travels home.
Thank you.